We've already talked quite a bit about how we can use the force to figure out the potential energy, but it turns out it's often nice to go the other way. So we know that the potential energy at a point is equal to the integral, the negative integral, from some reference point where we've defined the potential energy to be 0, 2x, of f of, I'm going to call it x primed dx primed. Now this is a notation you'll see in physics fairly often. This x primed does not mean that it's the derivative of x in here. It's just to distinguish between the x we're using to integrate and the x that I have up here. I could have called this y, I could have called this z, I could have called it f of happy face d happy face. Now, if I take the derivative, though, of u with respect to x, well, the derivative of an integral, where it's with respect to the upper limit, is just the value inside at the upper limit. In other words, this is simply negative f of x. Or in other words, the force f of x is equal to minus du dx. That works in one dimension. They showed it in the book saying, well, what if it's just very small variation? If we did a very small variation, then we would say u of x is equal to u at some original position, x naught, plus f at the position delta x, where delta x was the change in position from our original position to here. And then we would say, excuse me, there's a minus here, not a plus. We would say that f of x is equal to delta u over delta x with a minus, and then we would take the limit as delta x became small. Either way of looking at it, it's clear that the force is minus the derivative with respect to x. That works really well in one dimension, which is all you really need to know for this class, but let's just talk about it briefly in a few more dimensions. It's a little challenging, but it'll help us next semester when we start dealing with electricity and magnetism, where we have to deal with potential energies that vary in all dimensions. In that case, we find that the force in the x direction is equal to the derivative of u with respect to x, the minus. The y component of force is the derivative of u with respect to y, the minus. And the z component is minus the derivative of u with respect to z. This little integral shape here means I'm going to take the derivative with respect to x, but I'm going to treat y and z as being constant. So I don't say derivative with respect to x plus derivative with respect to y times dy dx. Okay, no chain rule stuff. We just take the derivative with respect to x and leave y and z constant. It's called a partial derivative. The key point here is each component of force is just how quickly the potential energy is changing along that direction. So if we consider a potential energy graph like this, we're not going to worry about this line here just yet. We've got a potential energy graph. It's high and constant at the beginning, drops down, goes back up, drops down, goes back up. Well, the derivative of it is 0 at the beginning and at the end. So at those points, at the beginning and the end, the force is 0. Here, the derivative is negative. Force is the negative derivative of potential energy, so the force is positive. It gets a biggest slope somewhere in here, which is what we see right there. Drops back to 0 at this point. From x2 to x3, the slope is positive, meaning that the force will be negative. So we drop down like this. From 3 to 4, the slope is negative again, so the force goes positive, coming back to 0 at 4. And from 4 to 5, the slope is positive, so the force is negative. Now you may say, what's with this whole positive negative? Well, we already saw that it came before, because when a conservative force does negative work on something, it's storing up the work so that it can do positive work back out. So doing negative work gives it positive potential energy. Seen another way, if we were to imagine that we had a little ball rolling along here, in this position where it's got a negative slope, it would tend to roll down, which would move us to the right, the positive direction. Here, with a positive slope, we would tend to roll down, which is to the left. So in this region, where we tend to move to the right, that's a positive force pushing us to the right. In this region, where our tendency is to move to the left, it's a negative force pushing us to the left.